I am, so as you can see, I have just some announcements that I think are kind of, you know, potentially useful. So I have, instead of moving to machining, we're going to kind of switch things up a little bit. We're going to do powder metallurgy next. And so I will have slides out and also some, I have some video clips as well. So we're going to do powder metallurgy probably Thursday and Friday of this week, and then we'll move to machining. I will have a like a reading assignment for machining that will be due next week. I'll probably go ahead and get that assigned today or tomorrow. Again, in lab this week is going to be going through that solid cast tutorial. So it would be very helpful, helpful if solid cast is functioning on your computer. So if there's any issues, let's try to work on those today. My plan is for all of us, well, all of us in each lab section. So the people that are assigned to Tuesday and then Wednesday, let's meet in the Harley lab, which is S130. I know that the monitors in S130 I wasn't able to get my computer to work with the monitors, but it's a nice room. And I believe that I should be able to sort of go through the tutorial and we can get everybody in there. And again, make sure you have your laptop. We are going to be going through the tutorial, which is out on Canvas. I'll probably have some copies of it, but if you kind of are a paper person, that might be helpful to have. I have not input the grades for the exam, but they're graded and I will turn them back in lab. If I forget, please remind me. Okay, that's it for sort of the announcements. So let's move on to our sheet metal. Okay, awesome. So I think, again, good. So we did talk a little bit last week about sheet metal. And, you know, we talked about shearing as that metal separation process in a punch and die. When we define deformation, again, we're looking at defining bending as deformation around a single linear axis. And then forming is the more complicated type of deformation where we have multiple curves, axes, and we often, again, it's cup-like. And I do want to just, again, kind of emphasize or reiterate that stamping is that general term. So again, shearing is where we have that separation of metal by two blades. We do have a very distinctive edge with that deformation and fracture region. We looked at some sheared parts, and we almost always have a little bit of a burr, and there's that smooth area. Sometimes we refer to this burnished land as the deformation. That's kind of weird. So sometimes we refer to this as the deformation and fracture region, and then the burr is on that fracture side. And again, a couple pictures from what we would have seen in lab where we have both that deformation and fracture. So a sheared edge has a distinct side. Also, it's really important to recognize that it is not straight. So it is, there is sort of an angle to it. Again, we have the burr. Now, we did say that clearance was important. Proper clearance is related to sheet thickness and ductility of metal. So this means that as we move from one material to another, or from one thickness or gauge of sheet metal to another, we may have to adjust the press and adjust the tooling. So tooling is not necessarily universal. So there can be some reasons why we might have to change the tooling. And again, if the clearance is too small, we get the jagged edge. If it's too large, we get the burr.
Dr. Barnicki, you're not sharing your screen.
Oh, thank you. Very good. Good thing this is the review part. You know, I thought that was kind of weird because usually when I'm sharing my screen, I don't see as much of you guys. Okay, as I said, good thing I was on the review part here. And we have our shearing operations. We talked a little bit also about bending and the idea that bending is single axis deformation, and we'll come back to forming. Here is our pot handle. And again, the amount of deformation. So when we look at the bend radius, we're talking about this radius here. That is going to be related to the ductility. And so, you know, we taught one of the videos sort of talked about where you can actually fold over directly versus more of what's called the sort of the teardrop hem, where we can't get quite as tight. Now, we looked at this, and I think the last thing we talked about was sort of this orientation of the tight bend to the rolling direction. Let's kind of consider a little bit about something that's called spring back. Now, spring back is the recovery of elastic deformation. And so we know that if I actually have a stress strain curve, and I go into the plastic region, on deformation or on unloading, I am going to actually unload on the same slope as I load. So we are going to actually unload on the line that is parallel to the loading or has the slope of the modulus. And so what we now this is an exaggeration, but what we recognize is that whether we have elastic and plastic deformation, we are going to see that when we have unloading, the elastic deformation is recovered. And again, that is called spring back. Now, spring back has has areas where we really need to consider it. So what that means is, so if we are looking at rolling sheet metal, we recognize that the distance between the rolls is the that has both elastic and plastic deformation is not the sheet thickness, because the distance between the rolls is both plastic and elastic deformation. And so when the metal comes out of the rolls, it's actually going to recover that elastic deformation and get larger. We have to take this into account. And so what we need to realize is that we will see that the sheet thickness is slightly larger than the distance between the rolls. So if we want to get really, really good dimensional tolerances on our sheet metal, we have to know how much spring back we're going to get. And now in bending, what we see is that if we kind of bend like this, we're going to see that after unloading, this is going to kind of move a little bit. Your book talks about this. We don't really have the time here to go into a lot of detail on how to predict spring back and why in bending it's more of an issue. Part of that is because in bending we have both a neutral axis and we have compression and tension. But I do think it's really important to realize that when we are talking about sheet metal, that there is this recovery of elastic deformation. And sometimes we just overbend, so we bend more. There's also some things you can do in terms of balancing the elastic and the plastic deformation. So that's really more with spring back, recognizing that spring back is going to be sort of related to your yield strength and your modulus of elasticity, because it is just this recovery of that elastic deformation. Okay, here we talked about the inclusions and the rolling direction. We do have a few, again, bending operations. This one is called seaming, and so we just look at interlocking two pieces of sheet metal by a bending operation. And so there's just a couple different types of seaming, but again, this is a bending operation. We also have what we would call bead forming, and so we kind of bring the sheet in and we just form this bead. We can also, I think it's important to recognize that there is a piece of equipment called a press brake, and bending is often done in that press brake. So now let's move to forming. So forming is the more complicated of the deformation, and when we consider forming, and if I kind of come back to here, we do see that ductility just doesn't quite, ductility is not the greatest predictor of whether or not we can do a particular operation. And so when it comes to forming, we are going to look at and consider sort of a new material property. So again, we saw these particular examples in the lab. All of these start with a piece of sheet metal, and we can see that in some areas there's substantial deformation. And so again, we have this property that we want to look at that we call sheet metal formability. So formability is really, again, we're looking at the ability for the metal to, change shape without failure. Now, we kind of, I should actually read my slides because apparently I decided it was important enough to write it down. So again, it's the ability of the metal to undergo the desired shape change. A couple things. It's often a biaxial process. So we have, and sometimes it may even be triaxial, but we certainly have deformation in two planes, possibly like all three directions. We also need to recognize that failure is tearing, and we don't talk about fracture with sheet metal, we talk about tearing. But it's really very similar in that we actually see the material separating. However, necking, buckling and wrinkling are similar. So failure becomes defined in maybe, let's say, a more conservative way, whereas our ductility, just because the material's necking, ductility is when the material fractures. And so when we think about sheet metal and we think about this forming, we really see failure can occur prior to the tearing or fracture. It's more difficult to quantify. So I don't just have a number. I can't say, well, the formability of this particular material is 7. Well, when I'd need units, but we quantify it by what we call this forming limit diagram. So there's different ways to do it, but one of the ways that we're going to look at it is the forming limit diagram. And this is where we have, so that sort of that circle grid is part of what we have. And so what we have, or what we're going to look at, is we will have the strain conditions that we need to form the part, and then we'll have the strain conditions for the material itself. And so here we have the circle grid, and we looked at that, and we see that there are, it looks like there's a number of circles. Some have become ellipses, some have become larger circles. So we use a circle, and how a circle changes shape to get our dimensions for strain. And so we really work with strain or deformation here. So when we talk about a forming limit diagram, we need to sort of realize that we have the material property, and the material property is the forming limit diagram. And so the forming limit diagram is a collection of points where failure has occurred. And so this forming limit diagram for a particular material is essentially the property itself. And so it is a graph of the major strain on the vertical and the minor strain on the horizontal. And so when we look at this, we have something that looks like this. And so again, here we have our line. So this, let's say, is for material A. And we have this line right here. And you'll notice that we have major strain, and this goes from 0 to a positive number. Here we have minor strain. This is negative. This is positive. And so anything that is above the line has failed. Anything below the line is safe. So, and if you're thinking, wow, how do we get these numbers? Where do these come from? So we deform the material in various tests, and we look for the strain state at failure point. And so each point along this diagram, this line, is a failure. And so you may have to deform the material in different ways. And how you actually come up with this is a fairly involved process. But what you do is, again, you take a material, usually in strips, and oftentimes you do the circle, you put the circles on it, and then you attempt to get different strain states. And then you look at the location where failure has occurred, whether it's tearing, necking, or buckling or wrinkling, and you record what that major minor strain was, and then you plot those points. And again, anything above that would cause failure, anything below would be safe. So the line itself is our material property. And so if we again sort of look at what this means is, so if a circle, so if we start with circles, let's see, I'm going to change pen colors since I've learned how to do that. I'm so proud of myself. Okay, so if we end up with a circle that goes like that, here we have a positive major strain and a negative minor strain. Okay, so, and then if we have something that goes like this, here we have a positive major and a positive minor. And so you can again see over here, we have the negative minor strain, and here we have the positive. You may notice that the way this is looking, that we can get more overall deformation if we have that negative minor strain. And that's certainly the case. Okay, so again, every material has its own line. And we can talk about a material having higher formability, the higher the line is up. Now, one of the things that also gets a little complicated on some of these diagrams is we also have strain states. There's a strain state that we might call uniaxial tension. And that is this line, this dotted line. And so that's not associated with the material. That's just sort of saying, hey, this is uniaxial tension. If I have balanced biaxial tension, that's when the strains are equal. That would be this line, which is 45 degrees. We also have something that's called plane strain. And plane strain, interestingly enough, plane strain is like very, very challenging on the material. Plane strain is when you have only deformation in one direction on the sheet, and then we certainly have sheet thinning going on. Okay, so again, so we have our material property. And now, how do we use this? So we have our property, and we know that that property is the graph. So now we have to look at, well, what does it take to form a part? And so we then get the strain states needed to deform a part, and we compare that to our graph. And oftentimes we will do a circle grid analysis on the part shape, which is what we sort of see here. And so again, here we have this sheet that a bunch of circles were put on. And then after deformation, we'll notice that like here we have some positive major strain, positive minor strain. So we look around and we like measure the actual strain state. Here we have an example where, so here this went to a little bit more of an ellipse. So this would be a minor strain, negative minor strain. And so what we do is we can then plot on a particular diagram. And so this is, again, kind of complicated. Here we have our plane strain line, our simple tension, our shear, our balanced. And now we see aluminum, high strength steel, brass, and then the low carbon steel is the shaded blue line. So again, here we have the properties for 4 materials. There's also some computer programs that would allow us to get the strains that would be needed to form particular parts. So if we sort of look at the trunk lid, so like right in here, this kind of gives us an idea of all of the various strain states needed. The front fender, we're over here. We notice that we have less strain, the roof lid, and then the door panel. So it looks like this, the back fender in this particular region, or the trunk lid, has the, the most strain needed. Well, here is another forming limit diagram, and this is actually listed in our textbook. And we see that they're a little bit of an interesting kind of thing. So we've got some various materials, and we see most of the time we're going to have a little bit of a dip. Sometimes it's near plane strains. Oftentimes it's going to be a little bit into the positive strain. So we would see that the line that's the highest is going to have the best formability. Okay. Now, we have a couple ways of describing the deformation. And this is where we have to, again, think about, are we defining the type of deformation? And there is 3 sort of types of deformation that we will talk about. There's really 2 categories, and then the plane strain is sort of the 3rd one. So for plane strain, we see that we have the circle, and then after deformation, and I'm exaggerating all of this, we only have positive major strain, and there's 0 on the minor strain. And so this is can be a challenging kind of deformation, and we refer to that as plane strain. Now, if we look at having the circle expand in both directions, it doesn't necessarily have to expand the same in both directions, but when we see it expanding, this is, again, in lab, I mentioned, well, what is it like when a balloon expands? That is called stretching. So if we refer to the type of deformation as stretching, so the material is stretching and it's thinning, we often find that this is not a desirable type of deformation, because it means that our product, what we produce, is going to have thin areas in some places. If we see that we have the positive major strain and negative minor strain, then the material may not fit. And we refer to this as drawing, and there's no L in there. So if we say that that we prefer drawing over stretching, that basically refers to the type of deformation that we have. Okay, so let's do a little bit of work here, and let's do an example. So we have a part, and we put 5mm circles on the part, and in 5 different locations. After we deformed this part, we determined that this is the amount of deformation that was needed. And so we have 5 points that we are going to graph. So let's look first. So in region A, the circle went to having a, so our 5mm circle. So we started in all cases with 5mm. And so here afterwards, we were 9.25 and 2.96. Okay, so 9.25 minus 5 divided by 5. So we're 85% and negative 40, like around negative 41. Okay, so for region B, we didn't have as much deformation, but we're still in this, actually. So region B is going to be more like this, where here we're at 7. Here we're at 4.35. So minus 13 plus 40. Here, region C, again, our major one is 7, and our minor is 2.5. So here we're about 50 minus 50. Region D, we've gone larger in both directions. So we are, again, 7 and 6.45. And then region E, we are that plane strain where we're 25% and then 0. So here are 5 regions where we see in that particular region, this is the type of deformation we're going to need to form that part. So now let's plot it on our forming limit diagram. Okay, and so here, let's kind of look. So we have point A, 85, negative 40. Okay, so here we have, this is A. So here we have A. B is positive 40, negative 13. Okay. So there we have B. C is 49, negative 50, like right here. Well, that's kind of festive. We see that point C is pure shear. That's lovely. D is 40, but now we're positive 30, so we're right there. And then E is 25, 0. So E comes out to be right here. So the question is, let's look at this, and now let's say that we have these points. How are we doing? Well, let's look at each of the materials. So if I look at, and we're going to look at low carbon steel, we're going to look at aluminum, and we're going to look at high strength steel. So if I look at my material up here, well, everything is below the line. So for low carbon steel, everything looks good. All the points are below the line. All the points are in that safe region. Well, let's look at the next material, high strength steel. Okay. And point A is a little close to the line, but I think that's okay. Again, if we started to see in production that we were starting to have some problems with failure, it could be that particular location. And there are some things that we can then look at doing to improve it. Now, let's look at aluminum. Well, here's our aluminum line. Well, this point is above, this point is above, these 2 points are on the line. Only this pure shear would be good. So aluminum would be aluminum would be a really bad choice because point A and D are above the line. So those are definitely going to fail. And then point B and E are on the line. And that's really, really tricky for this. And so here's how this forming limit diagram works, where we have the type of deformation that we need to form the part. We then plot it or compare it to the material, and we determine whether the material will function or not. Now, what's interesting is that you'll notice that when we look at this particular, diagram, that this is the aluminum. Here's our low carbon steel. The formability of aluminum is actually lower than that of steel. And that might seem kind of odd. A lot of this work came when there was a big push. There was a big push maybe 30 years ago to try and reduce the weight of vehicles. And a lot has happened in this time frame. There's a lot more plastic that's in materials, but there was really this thought that if a lot of the steel components could be moved to aluminum, you could have a substantial reduction in weight. And that is the case. There are some challenges with aluminum. We know that aluminum has a high specific strength, meaning its strength to weight, but the modulus of aluminum is a third of that of steel. So you have some challenges there. There also was some challenges with the formability of aluminum. So you cannot just take the same, let's call it stamping dies that you have been using for steel and use it on aluminum, because in some cases you may have way too much deformation. And so a lot of this work that we're talking about was developed in response to that, looking at moving from steel to aluminum. And it's really, though, as manufacturing has moved from the sort of the artisan, I think that's close enough, we're continuing to look at ways that we can model and quantify these more elusive properties. So anyways, this is how that whole forming limit diagram is going to work. Okay, now I want to finish off with some, a couple process things. And so you may have, I believe in the video, especially the sheet metal, they talk about this is something that's been deep drawn, or this is a drawn part. Well, there is a process that is called drawing. And we may actually, sometimes we look at that particular process. So we see that it is a process and also a type of deformation. So when we say that drawing is a type of deformation, it means the sheet is deformed without thinning. So this is going to be a positive major and a negative minor on strain. So we're talking about a type of deformation and where it fits on the forming limit diagram. There's also what we call, and a lot of times we say deep drawing. It's a process. And that's where we create a box or a cylinder, cylindrical or box-shaped parts, with the whole concept being that the thickness of the sheet doesn't change. We're just sort of flowing it in. It usually occurs as a punch presses a blank into a die cavity. And it's actually, the analysis of it and some of the material considerations can become quite complex. We often form cans, sinks, containers, and again, we're usually looking at a blank, so we're a sheared, the punch comes down, flows the material into the die, and then we get our drawn cup or our deformed cup. So again, this is a process that we might talk about. Okay, so let's finish with a few sheet metal design considerations. And we just want to kind of look at some of the good and the bad on here. So we want to look at, again, waste, like how do we have the most efficient, and then that would be in blanking. So if we can have parts that nest, so there's no waste here. So if we kind of look at the better, we see that these parts on the right, they may function in the same manner in that we have holes that are aligned in the same location. This would have no waste, whereas over here we have more shearing and a little more waste. Same with these two. Again, if what's important is the relative location of the holes, the ones over here on the right under the better, we have far less waste, and it's just a more efficient process. We can't always do this, but if we can, this is a little helpful. So again, when we think about what the function of the part is, if you can achieve that same function and have the parts be able to nest, it's just nicer. And then on bending, we just want to look at three concepts: relief notches, orientation, and then stress in the bend radius. One of the things that we do, if you kind of think about what happens in bending, you actually have some elongation. And so when you bend and you have a closed corner, you can actually get some stresses. So what we find is that if we remove some material and we actually put in a full notch, we're able to make this bend without as much buckling or tearing or other processes. So relief notches are always good. Again, we have some examples of putting notches in. We just sort of see that we've got the notches. It just allows for better bending. And again, this does go back to like how the neutral axis changes in bending, and you actually have a little bit of lengthening when you do bend. And then again, we do see that we can reduce the stress concentration by, again, allowing some a little bit of extra material. So if we're too constrained in bending, we can have some problems with that. Okay, so that, let me figure out where my cursor is. That is finishes up our sheet metal, and we will